I would say good afternoon, all of you. So this is lecture number, I would say 32 of the course Digital Communication. So I am completing the remaining portions from the syllabus for the NSIM. So let us see what we did in our last lecture or in our last interaction before we had the last lecture of the course or the last lecture in the semester. So we derived this error probability for QPSK, okay, and this was more or less inspired or done via a different, you can say, methodology where we equated or where we found out that the coherent QPSK is equivalent to two coherent BPSK systems, okay. Now, coherent word, we know that it means that at the transmitter as well as at the receiver, the carrier is of the exact same frequency and same phase. Okay, so that is called as a coherent system where at the transmitter and receiver carriers are well synchronized in the sense that they have same frequency, same phase. So the benefit is that at the receiver you can multiply or you can do a correlation of the received signal with the carrier, and you can generate its projection on the signal space, and then you can build a decision logic on that. So coherent QPSK is equivalent to two coherent BPSK systems where these two BPSK systems can work individually or independently. Why? Because we found out that this is the way. So if we say 1 is 1 and minus 1 is 0, so I basically what I do is that there is an input bit stream. I divide it into two parts. One is the odd numbered bits and one is the even numbered bits. Now these odd numbered sequence and this even numbered sequence can be encoded individually through the BPSK system. So 1 is 1, 0 becomes minus 1, and we have now the QPSK system. We simply add the output of both of the coherent BPSK systems. So you will see the figure through the textbook in let us say 3-4 minutes ahead. So we were basically deriving this error probability over QPSK, found out that this is given by this. This ERFC function, we already know what it is, and it has been discussed in some of our earlier lectures. So let us first of all resolve a few issues. Okay. So resolution of a few issues. Resolution of a few issues / concepts / doubts. Okay, so doubt number 1, let us call it D1. Okay, so let us see the textbook. So in the textbook, we find out that this is the way they have demonstrated the QPSK system. Okay, so what they have done is essentially, let us see, I think there is the figure for it. Let me check it out. Yes, it is figure 6.8, page 359 or 359. Yes, this is. So what they do is that, let us say there is a binary data sequence which is giving you a sequence of zeros and ones. You convert it to a sequence of 1 and minus 1 through this polar NRZ level encoder. This we know what is a polar NRZ waveform. Then you apply it to a demultiplexer. Now what it will do is, let us see that. So you have this, let us say this is plus 1, then this is minus 1. Then this is plus 1, then this is suppose minus 1 for 2 instances, this is plus 1 for 2 instances, then this is this, okay, this is 1, minus 1, 1, minus 1, minus 1, 1, 1, minus 1, 1, 1, okay. So demultiplexer, what it will do is that it will take this, so this is bit stream 1, so B1, B1, then this is B1, then this is B1, and this is B1. Okay, so B1 is what? So the input stream was minus 1, 1, minus 1, minus 1. Sorry. Okay, so this is the stream. So it gets divided into two streams. So stream 1, this is bit 1, or stream 1 you can say, is 1, 1, is this minus 1, then 1. This, and this. Okay, 1 plus 1 minus 1, 1 and 1, and the bit stream 2 is the remaining thing, that is minus 1, minus 1, 1, minus 1 and 1. Okay, so but the impact on this is that if this bit interval was TB, The bit interval for B1 will be 2 TB. 2 TB is now the bit interval. Why? Because let us say for this duration, this -1 goes to second string. Okay. So now this bit, that this +1 is present for 2 bit times. Okay. So ये ऐसे हो जाएगा, +1 is present for 2 bit times, and then +1 is present for another 2 bit times. So this is, let us say, TB. This is TB. Then this is also TB. Okay. So +1, then -1 for 2 bit times. This is TB. Okay. So -1, and then this is +1 for 2 TB. So this is the way this B1 is. So this is a diagram for B1. So 2B is now the bit interval. Why? Because you have demultiplexed that. So once you demultiplex, so suppose this is 1, this is 0, this is 1, this is 0, and this is 1. So you are saying that I am demultiplexing. So this 1, if it goes here, so it is going after TB, this 0 comes. Okay. So for TB plus TB times, this 1 is maintained. So this should be remembered. Suppose this comes, this is 0 time, then this is TB time, then this is 2 TB, then this is 3 TB, this is suppose 4 TB. So 1 comes. So at a 0 time, 1 is coming. Now it is waiting for, at 0 time, it is waiting for TB duration. Okay. In TB duration, 0 is come. Then 0 is maintained for TB. So this is maintained for another TB. And then 1 comes. Another 1 will come at this point. So for 2 TB times, this 1 is there. Similarly, for 2 TB times, this 0 is there. Now the question is, why doubt I have raised is, if you go back and see this diagram. So what they do is that they have this odd number sequence and this even number sequence. They have drawn the respective BPSK waveforms, and then they say that we add both of them to generate the QPSK waveform. Now there is a doubt. I said that we choose f of c as some integral multiple of the TB. Okay, f of c as, or t. In the case of QPSK, we will choose it fc is equal to n upon t, where t is the symbol period. Now, with that, in that case, the question is, do we maintain odd or even number of cycles in each symbol time? So from this figure, it is not yet clear, but yes, it is. See this. We have not yet, if I refer to figures, okay, so in figure, doubt is in figure 6.7c, can we locate that we have odd / even number of cycles? Oh, I should not use odd, any integer number of cycles. This should be the better word. We have integer number of cycles in each symbol time t. So answer is yes. Sorry, let me just complete the question first. Okay, let me just complete the question first. The question is cycles as we choose f of c as some n of c by t. Answer is yes. We can see that the definition of cycle depends on the way we see it. How? Let us say this is one cycle. So this is the cosine waveform. I can take any 2 pi chunk of it and say that that is a cycle. Okay, I can take any chunk of length 2 pi and say that is a cycle. So if I suppose take from this, so I have to go to this, and this. This is the point where I will terminate. So this is one cycle. I can choose this is also one cycle. I can start from here. I can say that if I start from here, then this is another cycle. So there are several possible ways to define a cycle. We just have to take a chunk of length 2 pi, and that is what is happening in the figure. So I feel that this might lead to some confusion. That's why I have just discussed it. Okay. So now you can see the figure again. So here you can see. So if at all I start from this point, then I have two cycles up to this point. Okay, right? Because this is one cycle and then this is one cycle. Same you can see for each of the symbol time. So this was one of the doubts. Okay. Now let us go to second point. So this is D2. Okay. So D2 says that let us see the transmission and reception for again. Okay. So this is a page number 359. Yes. So we are now very much clear that this T is 2 TB. You must remember this T is 2 TB. Let me tell you. In QPSK, symbol time T is equal to twice of TB. Why? Because you are taking two bits together to represent one symbol. Okay. So two bits they are coming sequentially at a rate of they are coming sequentially with each bit taking TB times. तो आपको दो bits चाहिए एक symbol बनाने के लिए. तो वो दो बिट्स के लिए आपको दो टीबी टाइम्स वेट करना पड़ेगा. तो एक सिंबल आपका 2 टीबी का विड्थ लेगा. ठीक है. अब हम समझ गए कि डीमल्टीप्लेक्स करके हमने दो स्ट्रीम्स बनाई, उन दोनों को अपने अपने बेसिस फंक्शन से हमने मल्टीप्लाई किया, या आप कह सकते हैं कैरियर वेवफॉर्म से मल्टीप्लाई किया, क्योंकि ये बीपीएस के सिस्टम है, ये कॉस है और ये क्वाड्रेचर कैरियर है. तो क्वाड्रेचर कैरियर में बीपीएस के. ठीक है. तो वो करके हमने ऐड कर दिया एंड वी जनरेट दिस क्यूपीएस के सिग्नल. नाउ एट द रिसीवर व्हाट डू वी डू इज that we do the correlation because we are in the coherent setting. Coherent setting means that phi 1t and phi 2t are available in exact form. So we will do the projection on each of the functions, and that projection is completed by multiplying and then integrating over the symbol time. So that is what is done. So you get two numbers x1 and x2. Now we know this encoding procedure. This procedure and this procedure is independent. So what do? We independently decide on x1 and x2, that whether x1 was 0 or 1 or x2 was 0 or 1. Based on that, we can then multiplex and say what is the estimated binary sequence was, or what is the estimated binary sequence is, which was transmitted. Okay. Now in this, there is one thing to notice, that what is the pulse shape. Okay. What is the pulse shape? What is the pulse shape we have used to study? So the answer is direct pulse, the standard rectangular pulse, of width 2 TB and amplitude root of EB on each of the carriers. That is, so what is this? So this is like this. 2 TB is the width and this is root of EB. Okay. So this says that, let us see this. So we know that, so this follows because E is twice of EB. Okay, this you must know, because if at all there are two streams, if at all this is taking a value EB and this is taking a energy root of EB, so they must add up, because our carriers are at quadrature to give you the energy of a symbol which is twice of EB. Okay, we will see it. Okay, 6.31. Okay, let me just go back to the textbook and refer to a Yes, let us go back and see the textbook. 357. 357, yes, here it is. So the signal energy per bit is E by 2 and noise spectral density is N naught by 2. Anyways, noise is, it adds to each of the quadrature carriers, or you can say that we have seen that WT is, if at all it is a wide Gaussian noise process, we sample it, then it has a variance of N naught by 2. Okay. So this way you can just study, or you can see it here as well, that this x1 is nothing but root plus minus root of e by 2, and this is plus minus plus root of e by 2. So if I take the sum of it, it is e, and this is nothing but eb, root of eb. So eb is e by 2. So there are several ways to see it. So I just told you this, okay. I can do a small derivation also to make it more clear, but I feel should be easy. Okay, and this is logical as well, that if at all E is the symbol energy, then EB and EB, if they are the bit energies, then both EB should add up to give you E. Okay, so this should be seen very clearly. Or if at all you want us to do a derivation, let us see this. Okay, let me do it. So we said that your SIT is nothing but root of twice of E by T cosine of 2y minus 1 pi by 4 cos of 2 pi fct minus root of twice of E by T sine of 2y minus 1 pi by 4 sine of 2 pi fct. Okay, where our time of consideration is 0 to capital T. Now you know that this will take a value which is plus minus, so you can say root of 2e by 2, sorry, root of twice of e by t. Okay, so you will say this is equal to twice of e by t plus minus 1 by root 2. Okay, cos of 2 pi fct minus root of twice of e by 2 minus plus 1 by root 2 into sine of 2 pi fct. Okay. Now what it is, if I take plus minus outside and I take this inside, so this is root of e by t cos of pi fct and minus, let's take this minus plus, we will take okay. So this is what is your net transmitted signal is. Let me just go back and see one thing. So if you compare, so what is a BPSK? For BPSK, the SIT is plus minus root of twice of EB by TB cos of 2 pi fct, okay, where t lies from 0 to TB. Now if I compare it with this system, now this is nothing but a BPSK system with capital TS twice of TB, okay, or we have to set TB as T, so over T this, or over you can say T this is equal to plus minus because TB is arbitrary here. So I can choose TB as T as well. So what is this is it. Now if I compare both of them, you just compare this 1 with 2. What do you get? That E is twice of EB. Okay, the symbol energy would be nothing but twice of EB. It has to be. But this is one way to see it. Another way to see it is you just derive this energy. You take SI square and integrate it over from 0 to capital T. Okay, so one issue is this. And then finally, we have to discuss your third doubt or third thing which I feel is important at this point to discuss. I think this is the third thing only. D of 2 we have done. Yes, so this is D of 3. Okay. So I think this is mapping I feel is okay. So we have one possible mapping is like this. Okay. So this is 1 1. This is 0 1. This is the standard you can say 1 0. Now how do you get that? See if in the NDV if I call the equivalent, so QPSK is equivalent to 2 BPSK operating independently over carriers that are quadrature to each that are at quadrature. It means the cos and then sine. Sine is pi by 2. Pi by 2 is nothing but 1 by 4 of 2 pi. Okay. So 2 pi का quadrature है pi by 2. So इसलिए cooperating independently over carriers that are at quadrature. So अब अगर हमने 1 को भी encode as +1 and 0 को encode as -1. Okay, and then I use this plus and minus logic or this NRZ waveform. If I use it, okay, to basically modulate each of the carriers and add, then what I will land at. So this is +1 +1. This point is +1 and +1. Okay, then this is nothing but -1 and +1. So this is the mapping. Then with this as the logic, with the logic in right. Logic in right, that is here, the gray mapping this is NRZ logic, polar NRZ. The gray mapping is as given above. Okay, in case you want to do a different sort of a mapping, it means you want to say that this is my 0 0, then this is my 0 1, this is my 1 0, this is 1 1. You have to use a different sort of a plus minus 1 mapping of 1 and 0s. Okay, so it means if you have to change this, then you have to, we do not want to, you do not have to use this polar NRZ, you have to use a different mapper, and that mapper would basically dictate a different sort of a mapping which you will choose. So that is important. Okay, so for a different gray mapping, the mapper needs to be changed. Or some different thing has to be done to incorporate that. Yes, and the last thing is important is where does pulse come into role? So here we have not yet talked about pulse. Let me respond to it. So the answer to this is we have used rectangular pulses up to now. Okay. We know that the pulse dictates the frequency consumption or frequency usage of the transmitted waveform. Okay. Okay. So if at all we need to tailor that, you can choose different shapes. Okay. This you can see in the Nyquist design criteria which we have done, okay, which we have studied. Okay, so let us now come to the M-ARRY PSK. So with this as a doubt I have done, so let us come to the concept of M-ARRY PSK. Now M-ARRY simply means that you have M possible phase points. So instead of the 4 values, carrier takes on one of the M possible values. Okay. For that, so theta I will be twice of I minus 1 into pi by capital M. Or the way to see it is you divide 2 pi into capital M points, equidistant capital M points, and then you add the index, that is I minus 1, where I will lie from 1 to up to capital M. Okay, because for 1 it is 0, and for 2 it will be 2 pi by M, then for 3 it will be 2 into 2 pi by M, then 4 into 2 pi by M, and up to 2 pi it will go. Okay, so 0 to, sorry, it will go up to 0 to 2. So let me write it down. So theta I versus I. So this 1, 2, suppose this is M. Okay, so this for 1 it is 0. For this it is 2 pi by M, then it is 2 into 2 pi by M, and this goes up to 2 pi by M into M minus 1. Okay. Let me just write it in more, you can say, clear manner. That is 2 into, and this goes on. Okay. So this is like this. So SIT is what? So SIT, that is the waveforms over the symbol time, which you choose is nothing but twice of E upon T cos of 2 pi of CT plus 2 pi by capital M I minus 1. Okay. Note that in QPSK we took theta I as, there is a difference. Now if I set for M as 4 here, it means if I try to derive the QPSK which I have studied, if I try to bring the equivalence between that the 4 array PSK is nothing but QPSK. So let us choose MS4. So here if you choose MS4, so your theta 0 would be for theta 0 to 0, theta 1 would be pi by 2, theta 2 would be pi by 2 into 2, that is pi, and theta 3 would be, let us say it is pi by 2 to 3 pi by 2. Okay, so let us check. This gives you this QPSK. So 1 is 0, so this is 0. then it is pi by 2 and this is pi by 2, and then this is pi, so this comes here, and then this is 3 pi by 2 and this is here. Okay. So, but we have studied what? We have studied this. Both are equivalent, okay? And it's an important question that which one should be preferred, what should we do, but we are not going to answer these questions right now because we have not much time left. Otherwise, we would have done this discussion. This is a good discussion to do. Although this also has 4 phases, this also has 4 phases, but you can say this is a rotated version of this. If you rotate this by pi